In this lecture video, we'll learn about various properties of logarithms. We'll begin with the product rule, which states that for any positive real number b other than 1 and any real positive numbers x and y, log base b of x plus log base b of y is equal to log base b of the product x times y. This follows directly from properties of exponents. If we let capital M equal log base b of x, and capital N equal log base b of y, then in exponential form, we have that b to the m is equal to x, and b to the n is equal to y. If we take the product of x and y, then we have the product of b to the m and b to the n. Using our properties of exponents, we have that the product of x and y is equal to b raised to the exponent of m plus n. Now switching this to logarithmic form, we have that log base b of the product of x and y is equal to m plus n. And unsubstituting m and n, we have that log base b of x times y is equal to log base b of x plus log base b of y. Let's use this property for a couple of examples. First, in example 1, we're going to take these two logarithms and rewrite them as a single logarithm. We have log base 2 of x plus log base 2 of y. It's important to notice that these two logarithms have the same base, so we can rewrite this as a single logarithm of base 2 of the product of x and y. In example 2, we will take this single logarithm and rewrite it as the sum of two or more logarithms. Here we have the natural log of 5 times x. Recall that natural log is equivalent to log base e, so we have log base e of 5 times x. And rewriting this as the sum of two logarithms, we have the natural log of 5 plus the natural log of x. Now let's learn about the quotient rule. The quotient rule says that for any positive real number b other than 1 and any positive real numbers x and y, log base b of x minus log base b of y is equal to log base b of the quotient x over y. This again follows directly from our properties of exponents. If we again let m equal log base b of x and n equal log base b of y, then b to the m is equal to x and b to the n is equal to y. And the quotient x divided by y is equal to b to the m divided by b to the n. And using our properties of exponents, we have that x divided by y is equal to b raised to the exponent of m minus n. Switching this back to logarithmic form, we have log base b of x over y is equal to m minus n. Unsubstituting for our variables m and n, we have that log base b of x over y is equal to log base b of x minus log base b of y, which is exactly the quotient rule. Let's take a look at some examples. In example 3, we have two logarithms that we will rewrite as a single logarithm using the quotient rule. Since both of these logarithms are base 2, we can rewrite this as a single logarithm, log base 2, of the quotient 40 over 5. 40 divided by 5 is 8, so this is log base 2 of 8. Log base 2 of 8 asks the question, 2 raised to what exponent equals 8? Well, 2 to the third is equal to 8, so log base 2 of 8 is 3. In example 4, we will rewrite this in terms of two logarithms using the quotient rule. Remember that natural log is log base e. We can first rewrite this as the natural log of the numerator, a times b, minus the natural log of the denominator, c. Notice that we can also rewrite the natural log of a times b using the product rule. In fact, we can split this into the natural log of a plus the natural log of b. So now we've rewritten this single logarithm in terms of three logarithms. Now let's learn the power rule. The power rule states that for any positive real number b other than 1, any real positive number x, and any real number r, log base b of x to the r is equal to r times log base b of x. In other words, we can take that exponent of r and move it out in front as a multiple of log base b of x. To see where this property comes from, consider log base b of x raised to the exponent of r. This is log base b of x times x times x for our factors of x. And using the product rule, this is log base b of x plus log base b of x plus log base b of x, and so on until we have r copies of log base b of x all added together, or r times log base b of x. Let's take a look at some examples. In example 5, we're going to rewrite using logarithms of single factors. We won't have any products or exponents inside the logarithm. Let's start by using the product rule. We can separate this logarithm as the sum of log base 2 of 16 and log base 2 of x to the 5th and log base 2 of y to the 12th. Consider that log base 2 of 16 asks the question 2 raised to what exponent is 16? Well, 2 to the 4th is 16, so this simplifies to 4. With log base 2 of x to the 5th, we can use the power rule. We'll take the exponent 5 and move it out in front, and have 5 times log base 2 of x. Using the power rule again, with log base 2 of y to the 12th, we have 12 times log base 2 of y. Now we've rewritten this logarithm using logarithms of only single factors. In example 6, we're going to do the opposite. We're going to rewrite this in such a way that the logarithm is not being multiplied by a number. In other words, we don't want this 8 out in front. Instead, we'll use the power rule in reverse and move the 8 up as an exponent of the x. In other words, this is equal to log base 8 of x to the 8th. In previous lessons, we have already noticed the property that log base b of b raised to the exponent of r is simply the exponent r. Think about what log base b of b to the r is saying. We're saying b raised to what exponent will be b raised to the exponent of r? Well, of course, we need to raise it to the exponent of r. We also have the property that b raised to the exponent of log base b of x is simply x. This follows directly from the fact that exponential and logarithmic functions are inverses. Those two functions undo each other, leaving us simply with x. Let's use these two properties to simplify the two expressions here in example 7. First, we have the natural log of e raised to the exponent of 6. Remember that natural log is equal to log base e, so we have log base e of e to the 6th. And since the base of the logarithm is the same as the base of the exponent, this simplifies to simply the exponent, 6. Now consider e raised to the exponent of the natural log of 16. Once again, since the natural log is log base e, we have e raised to the exponent of log base e of 16. The base of the logarithm matches the base of the exponent, so this simplifies and becomes 16. Now let's put all of these properties together and begin simplifying larger expressions. Here in example 8, we're going to rewrite these expressions as a single logarithm, assuming that all variables are positive numbers. Let's take a look at the natural log of 5 plus the natural log of a minus the natural log of b minus the natural log of c. One way to think about this is that the arguments of the logarithms that are being added will end up in the numerator, and the arguments of the logarithms that are being subtracted will end up in the denominator. Another way to think about this is to combine the last two terms and rewrite this expression as the natural log of 5 plus the natural log of a minus the natural log of b plus the natural log of c. Using the product rule with the natural log of 5 and the natural log of a, we have the natural log of 5 times a. And combining the natural log of b and the natural log of c, we have minus the natural log of b times c. Now we can clearly use the quotient rule and turn this into the natural log of 5a divided by b times c. Again, noticing that the arguments of the logarithms that were added, 5 and a, are in the numerator, and the arguments of the logarithms that were subtracted, b and c, are in the denominator. Let's take a look at this second expression. We have 1/2 times the logarithm of x plus 4 times the logarithm of y minus 3 times the logarithm of z. Since these logarithms do not have a base specified, we know that this is the common logarithm, log base 10. Before we can use the product and quotient rules to combine these logarithms as a single logarithm, we must first use the power rule. We need to move 1/2 from being a multiplier to an exponent. We need to move the 4 from being a multiplier to being an exponent, and we must move the 3 from being a multiplier to being an exponent of z. Rewriting these three terms, we have the logarithm of x raised to the exponent of 1/2 plus the logarithm of y raised to the exponent of 4 minus the logarithm of z raised to the exponent of 3. X to the 1/2 is the square root of x, so I'll quickly rewrite this. Using the product rule, I can combine these first two terms. This is log base 10 of y to the 4th times the square root of x. And using the quotient rule, we can combine this into a single logarithm. We have log base 10 of y to the 4th times the square root of x divided by z to the 3rd. Now let's do the same process in reverse. In example 9, we're going to rewrite this logarithm in terms of 2 or more logarithms. We won't be finished until each argument contains only a single factor and each exponent is written as a factor. Let's begin by using the quotient rule to write this logarithm as 2 logarithms. We'll have log base 2 of the numerator, 32x to the 7th, minus log base 2 of the denominator, y cubed. Now we can use the product rule with the first term and separate it into 2 logarithms. This is log base 2 of 32 plus log base 2 of x to the 7th. Now let's simplify each of these logarithms. First, we have log base 2 of 32. Since 2 to the 5th is 32, log base 2 of 32 is 5. Next, with log base 2 of x to the 7th, we can move that exponent of the x out in front as a factor. So we have 7 times log base 2 of x. And finally, with log base 2 of y to the 3rd, we can again move the exponent 3 out in front as a factor so that we have 3 times log base 2 of y. To finish this lesson, we're going to learn the change of base formula. The change of base formula for logarithms tells us that for any positive numbers, a, b, and x, with a and b not equal to 1, if we have log base b of x, we can write this as a logarithm with a different base, base a, as log base a of x divided by log base a of b. This allows us to rewrite logarithms in terms of common or natural logarithms. That way we can evaluate them using a calculator. Let's take a look at log base 4 of 42. Since there are no variables involved, we'd like to evaluate this, but 42 is not a simple power of 4. We'd like to use our calculators. Our calculators have the built-in functions for the common logarithm, log base 10, and the natural logarithm, log base e. I'll show you 2 different ways to use the change of base formula that will allow you to use your calculator. First, here's option 1. Let's switch to the common logarithm, log base 10. We have log base 4 of 42. To use the change of base formula and write this as log base 10, the numerator is log base 10 of the original argument, 42, and the denominator is log base 10 of the original base, 4. Log base 10, that's our common logarithm. We can even write this without the base. And this is something that we can evaluate using our calculators. Using our calculator and rounding to the nearest thousandth, this is approximately equal to 2.696. Consider that 4 squared is 16, and 4 to the 3rd is 64. So this makes sense that our answer, 2.696, is between 2 and 3. Now let's evaluate this same logarithm using the natural log. Instead of changing to the common logarithm, log base 10, let's change to the natural logarithm. That's log base e. We can rewrite this as log base e of the original argument, 42, divided by log base e of the original base, 4. Since this is log base e, let's just rewrite this using our natural log notation. Again, this is something we can put right into our calculators, and we find that rounding to the nearest thousandth, we have 2.696. Of course, the same answer as before. Again, this change of base formula allows us to take logarithms with any base and rewrite them with a different base, typically the common logarithm or the natural logarithm, so that we can evaluate with a calculator. That concludes this lecture video on some properties of logarithms.